this is the third lecture of module 1, neural networks. We have already discussed the linear neural network, system identification using the linear neural network. Then we talked about the feed-forward neural network, that is multi-layer network, which has capability of approximating any nonlinear function. And we learnt in the second lecture how to derive backpropagation algorithm for the feed-forward neural network that can approximate any nonlinear function. So, today in this third lecture we will again review the backpropagation algorithm that we derived in the last lecture. Then the generalized delta rule, we will understand this concept today. Then system identification using this backpropagation algorithm. Then two different variation in backpropagation algorithm, that is adding a momentum and adaptive learning rate. Today we will just have a very heuristic version of adaptive learning rate, and the next after 3-4 lectures probably we will have a detailed analysis on how to comprehensively design adaptive learning rate for backpropagation network. The reason being that this particular analysis would need the concepts of nonlinear stability for nonlinear systems, that is Lyapunov function and Lyapunov function based stability theory. So, these notions has to be reviewed before we can talk about a very comprehensive method of computing adaptive learning rate for backpropagation network. Okay. So, multi-layered feed-forward network that we have already discussed. We talked that you have input layer and then you have many layers, and these layers have many neurons. And these are all input signals coming here and they are fanned out. Okay, and this is your output layer, and these are all hidden layer. So, what we are saying that this is called multi-layered feed-forward network. It has more hidden layers of computation unit, that is these hidden layers can be more than one. So, you can have 1, 2, 3, 4, as many as you want. And in this feed-forward neural network, FNN stands for feed-forward neural network. So, the connections are allowed from one layer to succeeding layer in the forward direction, not in the backward direction. I cannot have a connection like this. This is not allowed. So, this connection is not allowed from this layer to this layer, but from this layer to this layer it is allowed. Hidden layer gets input from input layer and gives output to the next hidden layer or output layer after internal computation. This is a basic structure of feed-forward network. So, this is the notation we used in the last class about the backpropagation network. X is the input, V is the hidden node output, Y is the actual output, Wij this is the weight connection between ith unit of output layer and jth unit of hidden layer. Wjk is weight connecting jth unit of hidden layer and kth unit of input layer. So, this you can easily see that my x is input, which is p dimensional vector, and the summation that weights into the input signals, and they are all summed here, that sum is h. So, if I say h j, so h j is simply w j k x k sigma over k. So, this is your h j, and then V is after you go through this sigmoidal activation, that becomes your V. So, V j is simply 1 upon 1 plus e to the power minus h j, that is the after sigmoidal activation. And again as usual your output y, it is n dimensional output, and y I is you add all V 1. So, that is your, so this is we have shown here. So, V j is 1 upon 1 plus e to the power minus h j, where h j is w j k x k, k equal to 1 to p, and similarly final response y I is phi g I, which is 1 upon 1 plus e to the power minus g I, where g I is w I j V j. So, that is if I go back here, this I write here g, that means my g I is simply w I j into V j sigma. Okay. So, this is my this is sigma. Okay. So, what you are seeing is that w I j is the connection weights between output layer, this output layer, and the hidden layer, and w j k is the typical weight between hidden layer and the input layer. So, this is the notation we used in the last class. So, this is called forward phase. In forward phase we computed the output of the hidden unit and then output of the output unit, and then the back propagation given the patterns, input output pattern. So, my given input x, I know what is the desired target y d, and my network has a response y I. So, I compute a cost function E t, which is a quadratic cost function, and I use the gradient descent rule, which of this nature w I j t plus 1 is w I j t minus eta dou E t upon dou w I j t. We have already discussed a lot about gradient descent. So, this gradient descent we apply to compute the error back propagation. So, doing that, updating weights connecting output layer and hidden layer. So, this is the weight what we are focusing is w I j. You see that w I j we are talking about this weight. So, once I transfer the signal from x to y, then here my target is there, I compute the target error here, I back propagate it, I back propagate the target error. So, this is my E here at the target, and this target error is back propagated, and through back propagation I update what is w I j has to be updated. So, the what we derived is that to compute what is the weight update in w I j, we need to know compute what is dou E t upon dou w I j, and that gives me a formula dou E I t upon dou y I upon into dou y I upon dou w I j. That is because dou E upon dou w I j, how do I compute this? So, I know that E is summation of E I. So, hence differentiating E with respect to w I j means I differentiate E I with respect to w I j and take a sum, okay. And then individual E I is a function of y I. So, I differentiate E I with respect to dou y I, and then y I, which is a function of w I j, I differentiate that, and that is how I compute this partial derivative. Okay. So, here this is dou E upon dou y I t, which is half, because this function E I is simply y I d minus y I whole square. This is my E I. So, hence if you look at it here, half into 2 y I d minus y I into when you differentiate with respect to y I, so you get minus 1 here. Okay, that is very clear. Now, dou y I upon dou w I j is dou I upon dou g I, because we know that y I we found out this is 1 upon e to the power minus g I. So, that is we have already shown here. yi is a function of gi. So, while differentiating, obviously I will differentiate yi with respect to gi and then gi with wij. So, doing that way, finally I get this expression delta wij is eta yid minus yi 1 minus yi into vj. Okay. The weight update algorithm we wrote in a generalized format. wij t plus 1 is wij t eta delta I vj, and vj is the input. You can see is easily here when I am updating weights for wij, vj is my input to the weights in this layer. Okay. vj is the weight input to the weights in this layer, and my error is E, which is so the back propagated error that I am talking here is represented as delta I, and this delta I, which is the error back propagated from the output layer, is defined as yi 1 minus yi into the error at the output yid minus yi. So, this is called the back propagation algorithm. My weights are updated, the new weight is old weight plus eta error back propagated into the input signal to the connection. And similarly, so we derived for wij, now we are talking about wjk, and wjk was the weight vector or weight matrix between the hidden layer and input layer. So, when we can again go through the similar, we have already derived, I will not go I will not go through the detailed discussion. So, what we did is that when I differentiate E with respect to wjk, then I differentiate ei with respect to yi and yi with respect to wjk the similar manner, and ultimately we finally get a relationship which is again has a generalized form. Wjk t plus 1 is wjk t eta delta j xk. The similar format you see, the earlier one was wij t plus 1 was wij t plus eta delta I into vj. So, this is the weight update for the between output layer and hidden layer, and this is hidden layer and input layer, where input layer the input is xk and delta j, which is the back error back propagated from the output layer. So, this is the, you see the delta I is the error back propagated in the layer in the output layer, and you multiply the corresponding weights wij and do the summation, that is the total error back propagated from the output layer to the layer between input layer and hidden layer into vj 1 minus vj, this quantity which is delta j. So, this is the delta j is the back propagated error to the layer that is situated between hidden layer and input layer. So, now I will summarize what we saw in the back propagation algorithm. So, we have a typical input layer, the vector x, which is p by 1, and then a single hidden layer, the output is v, which is m by 1, this is p, and then the output layer, which output is y, and this is n by 1. So, let us consider a jth unit, jth computational unit in the hidden layer, ith computational unit in the output layer, and input layer kth computational unit. All right. So, what we saw in back propagation algorithm, W here wij t plus 1 is wij t plus eta delta I into Vj. So, what is Vj? This is the, so what is my Wij? This is my connection, this is Wij. So, this particular weight is updated based on the error on a single data set, instantaneous based on instantaneous update rule. What we do now, we update Wij based on its previous value, and the correction is eta is the learning rate, eta is learning rate. Normally this value is eta is 0 to 1. Delta I, this delta I is the error back propagated from the output to this output layer. I normally say this is the second layer, this is the first layer. So, let me say this is the second layer. Okay. So, delta I we found out the weight to be yi 1 minus yi into the error, that is y d I minus yi. So, this is my error at the output multiplied by yi into 1 minus yi is delta I, and Vj is the input, this is the Vj. So, if you look at Wij, the input is Vj to this connection weight, and the output of this unit is yi. So, given that the delta I has a unique structure, delta I is yi minus 1 minus yi d minus yi, and the update rule also has a unique structure, because Vj is the input to the connection weight, delta I is the error being back propagated through this weight, and this is a very, and this is called delta rule, that is the, in terms of the weight update rule has a very simple form, which is delta, which is error back propagated into input, and same thing also we will see here. This weight, which is Wjk by convention that we have already discussed. So, this is my xk, the output of this unit, and output of this unit is Vj. So, the weight update law we saw, which is Wjk t plus 1 is Wjk t plus eta delta j into xk. So, you see that this and this has the same form. So, that is why this is called delta rule. We can and of course, the delta j has a different value than delta k, but it has also a unique structure. Delta j is Vj 1 minus Vj into sigma delta I Wij over I. So, I add I, the output unit is 1 to n, delta I Wij multiply Vj 1 minus Vj. So, this is my error being propagated from this unit over this. This is the error delta j. So, this is delta j. So, delta j is being back propagated in this particular connection weight from this output layer. It is very important to understand. Okay? And delta j into xk, xk is the input to this connection weight. So, you can easily say that error back propagated in that particular connection weight into the input to that connection weight, if you multiply and multiply a learning rate, and that gives you the back propagation rule, and it is very simple rule. So, using this delta rule concept, we can write down this back propagation algorithm for any layered network, and that is what we will write now here in the next one. So, which is we will say generalized delta rule. We derived this delta rule for a single hidden layer. Now we will generalize this delta rule for any number of hidden layers in a feed forward network. So, that is why it is called generalized delta rule. So, let us consider, you see here we have a multi-layered neural network, and this multi-layered neural network has L layers. This is the input layer, first layer, second layer, third layer and L layer, and these are all feed forward network. These are all feed forward network. Okay. These are all feed forward network, and the index for each layer, like we earlier assumed I, j, k, I is the for output layer, j for hidden layer and k for input layer. So, similarly here the index we have little generalized, IL for lth layer, and so similarly II is for ith layer. So, I3 for third layer, I2 is for second layer. So, this is obviously for input layer the index is I0. Okay. So, with this particular convention we can easily now write down using the same whatever we discussed here our the normal delta rule. So, this is called delta rule because our weight update algorithm consists of the error back propagated into the input to the specific connection weight. So, this is delta rule. So, using that we can now write down the update rule. So, you see here this is my the weight, typical connection weight between L and L minus 1 layer, L and L minus 1 layer. So, that is what I am talking about here. This is my W I, this is my L and I L minus 1, the weights between this layer lth layer and the preceding layer, just preceding layer. So, we are talking about what is the, how do I update the weight in this layer. Once I pass the input through this network, compute the output at the output layer, compare with the desired data, and then I want to update this weight. So, the same formula. So, that is eta delta IL into V L IL minus 1. So, this is the input to this connection weight, and this is the error being back propagated. And obviously, you can easily see that delta IL. So, this L and this capital L and lowercase and uppercase are same. We are not discriminating. Okay. So, delta IL is YIL D minus YIL into this is our error at the output, and you have to multiply this term YIL into 1 minus YL. So, that transforms the error at the output to the when it is back propagated. So, this is this delta IL is here. So, this is error back propagated in this immediate layer. So, that is the lth layer. Okay. So, this for the output layer, and delta IL so okay, this L represents any layer. This is not, and delta IL is the for the capital L, that is the output layer. We have made some changes here. So, this you see that let WIL IL minus 1 denote the synaptic weight connection, synaptic weight connecting the ith neuron of layer L to that of layer L minus 1. So, this L is any typical layer. Considering sigmoidal function, activation function as the activation function for each layer, the weight update law can be written as, so this is for any layer. Okay. So, this particular weight is the weight between any of these layers. Okay. For example, if I take L equal to 2, then this is the layer. L equal to 3, then this is the layer. L equal to 1, then this is the layer. L equal to capital L, and this is the layer. Okay. So this is the general delta, generalized delta rule. This is a generalized delta rule. Okay. So given the delta at the output layer, we can easily compute corresponding delta in all preceding layers subsequently. Okay. And then we can update all the weights in all the layers using this concept of delta rule. I will give you a simple example. So let us explain this generalized delta rule through another example, a 4-layer network we will talk about. This is input layer, first layer, second layer, third layer, fourth layer. So obviously the weight between third layer and fourth layer will represent by W I4 I3. The weight between third layer and second layer W I3 I2. The weight between second layer and first layer and second layer is W I2 I1, and first layer input layer and first layer is W I1 I0. So this is our convention we are following. So given the error, that is y d minus y at the output layer. So how do we go? So naturally the element of y is y I4, okay, because I4 is the index for the output layer. So when I say y is a vector, y I4 is an element of the vector y, right. So y is the output vector. So this is weight update law for the output layer, that is the fourth layer. So this is my first layer, the second layer. When I talk about the in terms of weight, connection weight, so this is connection weight, first layer of connection weight, second layer of connection weight, third layer of connection weight, and fourth layer of connection weight. Okay. So as many layers we have, that many layers of connection weights we have. So what you are seeing here is that, as we saw earlier, W I4 I3 is the typical weight in this fourth layer, is updated using the generalized delta rule, which is eta. Delta is the error back propagated, and Vi3 is the input to the connection weight W I4 I3. So and what is delta I4? Delta I4 is obviously y I4 d minus y I4 into y I4 minus 1 minus y I4. This is my error that I computed here, and this is transformed. Because of the segmental activation function, we get this. If we have a linear activation function, this particular term will not be there. Okay. So this is the update rule for the last layer or the output fourth layer. And then the third layer, similarly, eta delta I3 V I2. Okay. So this is delta. So this is my delta I4 here. This is delta I3, delta I2, and delta I1. So I computed what is delta I4. Based on delta I4, I can compute what is delta I3. So this is what I will do. Delta I3 is Vi3 1 minus Vi3 into delta I4 Wi4 I3, and this is actually I4 equal to 1 to n, or whatever the number of units in my lth layer. Okay. Similarly, this is let me say this is n NL N4. So similarly this is N3. Okay. So weight update law for second layer, weight update law for the second layer will be similarly eta delta I2 Vi1. You can easily again check it. Delta for this delta I4 into Vi3. this is delta I3 Vi2, this is delta I2 Vi1, and this is delta I1 and Xi0, because here it is input layer Xi0. So, this is what we will have now. So, this is what you can easily see, eta delta I3 Vi2, this is for third layer, delta I2 Vi1 second layer, and this is your the error back propagated and based on delta I3. So, delta I2 is computed based on delta I3, delta I3 is computed based on delta I4, and similarly finally delta I1 is computed based on delta I2, and this is your the first layer. So, given any layer using generalized delta rule, we can write back propagation algorithm. We do not have to derive again, making all those complicated forward response equation and then differentiating the error with respect to each typical weight and finding all those complex. There is no need actually. This rule actually is generalized. We do not have to compute. They are actually the right formula. These represent the right formula. Okay. So, we are done. We are done with the first part here that we wanted to explain today is the generalized delta rule. So, in the generalized delta rule, the concept was that that we wanted a recursive formula for a back propagation learning algorithm. So, it allows the error signal of a lower layer to be computed as a linear combination of the error signal of the upper layer. In this manner, the error signals are back propagated through all the layers from the top down, that is from the last layer, the output layer, backward up to until input layer we reach. We can compute the error back propagated, which is in terms of delta, which is here. So, we have to compute here what is delta IL for the output layer, and based on that we finally compute what is delta I1. Okay. So, delta I1 is computed based on delta I2, delta I2 is computed based on delta I3, delta I3 is computed based on delta I4 and so forth. Finally, delta IL minus 1 is computed based on what is delta IL. And the normal the general form is that this is your general form between this is a typical weight between IL L layer and L minus 1 layer, and the update rule or delta W is eta delta IL into V IL N minus 1. So, what you are seeing is that eta delta IL V IL minus 1. So, this is our input to the connection weight, and this is the error back propagated to the layer L. So, using this concept, now we will demonstrate the application of back propagation algorithm for system identification. Since it is a control course, we would always use system identification for demonstrating any the application of a specific neural network. So, a practical system, a search tank system has been taken for simulation. We will identify the a search tank system using a neural network, or we will model the search tank. So, what is a search tank? Search tank, what you are looking at is that this is normally a search tank is used to control the hydraulic transient and pressure changes. Like for example, you see this is a big reservoir, and this reservoir, the water sometime the level increases suddenly or suddenly decreases, but this reservoir is connected particularly to say hydropower plant. So, and where the turbines has to move in a specific speed. Okay. So, the flow rate here has to be constant. So, if this reservoir the water level suddenly increases and suddenly decreases, then this flow rate will be affected. So, to to maintain this flow rate constant, the surge tank is used. So, what happens? So, whatever the disturbance in this reservoir level, that can be controlled using a surge tank. This whatever the extra pressure you have, this extra flow can be either can be pushed to the surge tank. Normally, this surge tank has a linear, has a nonlinear, the structure, means the level, that is it is if the surge tank is, the structure is like this, that means this is the cylindrical structure, okay, a cylindrical structure. That means the everywhere the diameter of this surge tank, say for example this is a circular thing, then the diameter is constant. But if the surge tank has a nonlinear structure, then given the specific flow into the surge tank, the water level in the surge tank, the water level in the surge tank and to the flow rate into the surge tank, they bear a nonlinear relationship. Okay. So, we would now we will try to model the surge tank, because unless we know how to model the surge tank, we cannot design, because we must know, given a specific water flow into the surge tank, how the level, water level in the surge tank is increasing or decreasing. Based on that, we will design a surge tank and specific dimension of the surge tank. Okay, how the diameter will vary linearly or non-linearly, all those things. So, we are just taking a nonlinear surge tank model. So, this is a schematic of a surge tank, the schematic diagram. So, when the pressure increases due to sudden change in the flow from the reservoir, the level of the surge tank increases, thus controlling the flow as well as the pressure to the connecting system. So, this flow is controlled accordingly. So, typically we are not interested now how we derive the model of a surge tank. What we are interested, that given a nonlinear structure of the surge tank, this is the dynamics of a surge tank, that is St plus 1 equal to St plus T is the sampling time, and this particular nonlinear, you can see easily this is a nonlinear function, because this is a square root of h, and also u is multiplied with 1 upon square root of h. So, hence this is a nonlinear function. So, t is the discrete time step, that is the sampling instant, first, second, third, fourth, fifth, okay, and t is the sampling time, ut is the input flow, and st is the liquid level in the surge tank, g is the acceleration due to gravity. Okay. So, this is our model of the surge tank. Why I am considering this model? Because in simulation we do not collect data from the actual surge tank, we collect data from a model, mathematical model in simulation. Okay. So, and using that data we will represent those data in terms of a neural network model, and this neural network model is the back propagation network that we have just learnt. So, what we have done is that we have taken this model and we generated data using this model, not using actual surge tank that is there in the field, okay, probably in the hydropower plant. We want to demonstrate the application of back propagation algorithm to a specific system modeling. So, this is a mathematical model of a surge tank, and using this mathematical model we generate data. Using that data we create a back propagation network. So, this you will see. So, what we have done here is that we have taken sampling time capital T is 0.01 in the mathematical model, and 150 data have been generated using the system equation. We saw that equation, this is the equation. So, using this equation, okay, so we generated 150 data. that is what is ut, given ut what is st plus 1. So, this is our input we have selected and this is the output, corresponding output. So, to that equation you set t equal to 0.01 and g is the normal acceleration due to gravity, which is 9.81 meter per second square. Once you give that parameter, here all other things are known. So, t is given 0.01, g you are giving. So, it is simply ut and ht. So, you given ut you compute what st using this particular equation. So, we used Runge-Kutta fourth order to generate the response. So, this response is generated using Runge-Kutta fourth order equation. This is actually, there is no need actually, this is a discrete time recursive equation. If it is a differential equation, then we would have used Runge-Kutta, but it is a simple recursive equation. So, there is no need for Runge-Kutta equation. So, we generated this data given this input, and then we selected a network structure and we took a backpropagation network having two hidden layers. Each hidden layer has 15 neurons or computational units, and number of output is the this is desired, whatever the desired that we got from the data is our, we have represent data in this term ut and h desired t plus 1. This we get from the system equation. Okay. So, this is my desired output h d t plus 1 given what is ut. But you can see here how we select. So, you see here in backpropagation network, feed forward network, if I give ut, I cannot compute st plus 1. You can easily see st plus 1 is a function of st as well as ut. So, st plus 1 is a function of ht and ut. All right. So, obviously, this st I take from the system, because at instant t I am able to measure what is the liquid level in the source tank. So, I am measuring that. So, that actual value I know what is HDT, and ut is the flow rate that I am able to measure, that is going to the source tank. So, given the actual liquid level of the source tank at time t and the flow rate at ut, I have to predict what is st plus 1. Okay. So, this is my model. So, obviously, to my system the input is ut and HDT, which is written here. This is actually D here, the desired, that which has been computed from the actual system. Okay. So, number of inputs I have 2 and output is my H desired t plus 1. So, given ut HDT, I must predict what is HDT plus 1. All right. So, that is the objective. So, we have fixed learning rate to be 0.2, number of input output data is 150, activation function for hidden layer is sigmoidal, activation function of the output layer is linear we have taken. Okay. So, we have two hidden layer. So, they are sigmoid and the output is linear, just, but you can select your own architecture and do the same thing. You can take actually, in fact, this can be easily done using a single hidden layer and output layer with sigmoidal activation function is easily we can do it. Just for so, what we do is that we have 150 training data, we selected a network architecture, we observed what is my input to the network and what is my output, and then we update the equation recursively. update the weights. So, in the beginning all the weights in the network were randomly initialized when very small values we took, and you see that the error has been reduced to less than 0.004 after 20,000 epoch. What is epoch? Each epoch is 150. That is, in my data set I have 150 different sets of data. That is, one data is my HDT, UT and HDT plus 1. Okay. This is my a single data set at T, and T equal to 1 to 150. So, I have like that 150 data set. So, I give to my network UT and HDT, compute what is HT plus 1, compare with the HDT plus 1 and back propagate the error and update the weight. And doing that I am able to reduce or make my cost function 0.004. So, after training is over, what we did, we give to the network a different control input, and compare with actual output, that is this control input was given to this equation, and then we computed what is the output. This is actual output based on this equation, and then we gave to the neural network that has been trained. And once we gave that this input to the neural network, and the response and the actual output based on the equation, they are actually matching, you can see here. So, you can see that there is a red line here and there is a green line. So, red line is the desired based on equation. So, red computed from equation and green from the neural network. Okay? And both red and green, they are very much following each other. So, in a sense we can say that the actual system identification has been done. That is, the equation that represents a specific a model of a specific search tank, that has been again represented using back propagation network having two hidden layers. So, now we will look into some other aspects of back propagation, that is the variation. Some problems in back propagation is that, as I already told you, the normal back propagation, it can only optimize if my cost function has a single minima, but normally my cost function will have many local minima as well as global minima. So, I may reach here, because if I start from here I will reach here. If my weights initial weights are here, then I will reach here, because that is the gradient descent. If my initial weights are here, I will reach here. So, this is the limitation of back propagation. Okay? So, reaching global minimum in back propagation is not guaranteed. That is why there is certain variations researchers have introduced in back propagation algorithm. First is improve the conversion speed, avoid local minima, and the generalization capability. Generalization capability means if I have trained my network for a specific data set, it should be able to predict for new data set what is the output. That is called generalization. So, one of the way to improve the conversion speed is the adding a momentum. How do we add a momentum? So, this is our equation. This is actually a heuristic approach, but we can analyze this equation just immediately. So, you see what is this is our normal equation, Wt plus 1 is Wt minus eta del E by del Wt. This is our normal gradient descent. Then I have added a momentum term, which is alpha Wt minus 1. So, when I add this is a heuristic, there is nothing, no derivation here. We have not derived this particular term. This is a heuristic. But let us see what happens, objectively analyze this equation in a flat surface. What is a flat surface? In flat surface, Wt minus Wt minus 1 is same as Wt plus 1 minus Wt. This is called flat surface. Okay. So, that is, say for example, sometime in my error curve is like this. So, I am moving like this. This is a flat error surface. So, if somehow I am here, I do not want to stay in the flat surface, I want to come back to the valley, I must go towards valley region. So, my speed should be very fast in this zone. So, in that case Wt plus 1 minus Wt is same as Wt minus 1, which is delta W. So, if that is the case, I can rewrite this equation, which is now, if I rewrite this equation, this is 1 minus alpha delta W, which is delta W is Wt plus 1 minus Wt, and say this is also same as, this is also delta. So, this is my delta W, and Wt plus 1 minus Wt also delta W. So, 1 minus alpha delta W is minus eta del E upon del Wt. So, once you look at this equation, then I write down what is my weight update delta W, increment in weight is minus eta upon 1 minus alpha delta E by del Wt. So, if you look at, then normally delta W is eta del E upon del Wt, but introducing this heuristic term, I am able to increase the learning rate by a term called eta by 1 minus alpha, and alpha is less than 1. So, obviously, if I say alpha is 0.5, then 1 minus 0.5 is 0.5. So, effective increase in the learning rate is twice. If I make alpha is 0.9, then 1 minus 0.9 is 0.1. So, effective eta is now 10 times the actual eta. So, the learning rate is thus increased by a factor by 1 minus alpha in the flat error surface. So, this is called how we can increase the conversion speed, and this is an example. This is an XOR network, and in the XOR network we have taken eta equal to 0.5, this is learning rate, and alpha is the momentum rate 0.8, and you can easily see here when we use the simple gradient descent, we do not use the momentum rate. My number of iteration is 4200. I take 4200 iterations to converge. That is, my RMS error is less than 0.0005, and for the same reaching the same termination condition with the momentum, I require only 2200. So, almost half of the means you adding a momentum, I could reduce the number of training is by half. So, this is called the speed of convergence. The convergence speed is almost doubled using this momentum term. It is not always, it is not that always by adding momentum I can increase the convergence speed, but some cases, because it is a heuristic, it is not always true. Similarly, adaptive learning rate, for this we will have a special class, but today I will just give a simple note how we implement adaptive learning rate by a heuristic manner. So, a heuristic approach to adaptive learning rule. So, you see that in a back propagation, eta is a fixed value. Once eta is fixed, most likely you will be in local minima, but if I vary this eta in a very intelligent manner in such a way, it can avoid the local minimum. This is called adaptive learning rate. Can I do that? So, here is a heuristic approach for which we do not have a theoretical basis. Simple, based on certain intuition, we derive this algorithm. So, what this particular heuristic algorithm is, a different learning rate is assigned to each adjustable parameter, that is, every typical Wij is associated with a different eta. Each learning rate parameter should be allowed to vary from iteration to iteration. when the derivative of cost function with respect to weight has same algebraic sign for several consecutive iterations, the learning rate parameter for that weight should be increased. Okay. When the algebraic sign of the derivative alternates consecutively for several iterations, the learning rate parameter should be reduced. So, what I am talking about now, we compute always a del E by del Wij, where Wij is typical weight. So, if this derivative is constantly positive, then for that particular Wij I increase the eta, and if this derivative alternates, sometime positive then negative, positive negative, positive negative, then what I do, I decrease this weight. This is the heuristic we introduce, and based on that heuristic, this is my adaptive learning rate. Eta I p t is mu eta I p t minus 1, okay, and d eta I p t minus 1. So, whereas mu and d are an increase and a decrease factor respectively. So, I either increase this by mu or I decrease the previous eta by d. This is a factor, okay, a multiplication factor. So, I either increase it or I decrease it. So, you see that the increase factor means it has to be greater than 1, decrease factor means it has to be less than 1. So, we have taken mu to be 1.1 and d to be 0.7, and we have taken the same exerve function, and now using the adaptive learning rate, and training is done until the root mean square error is less than 0.0004 for the exerve gate. So, we finally we see that without adaptive rate, as we have already seen, the 4200, the simple gradient descent gives you 4200 number of iterations or training samples, or that many times I have to update the weights, 4200 times I have to update the weights. Whereas using the this heuristic adaptive learning rule, we could reduce that to 1300, okay, for the same root mean square error, reaching the same root mean square error. So, finally, to conclude, I would say what we discussed today is that we reviewed what is back propagation, we reviewed back propagation, we talked about generalized rule, then we talked about a system identification, of a search tank, and then we talked about adding a momentum, this is to increase the conversion speed, and to avoid to increase the conversion speed as well as avoid local minimum also, we talked about a heuristic adaptive learning rule. And we will take a special class on adaptive learning rule in detail, how to comprehensively using a having a theoretical basis, how we can compute this adaptive learning rule, probably after 2-3 classes. But this is the summary of today's class. Thank you very much.